We're going to look at graphing quadratic equations, and of course when we say quadratic equation we mean an equation in the form y equal to ax squared plus bx plus c, and we're going to want to let a and b and c be elements of the real numbers, and we do not want to let a be 0, because if a was 0 this term would be gone and we'd have nothing but a linear equation left over. We want to look at graphing them, and as we look at graphing them there's a couple of values here, the a and the c in particular, that we want to look at what they do to the graph. Now our standard graph, which we will always compare to, is y equal x squared. When we say, a graph has been moved or changed in some way, this is the original graph that we're talking about. Now I want to look at various values, first of all for a, to see what effect a has upon the graph. The easiest way to see this is on the calculator. So let's hit the y equal 2 button, put in x squared, which again is the graph we always compare to, and when we do a zoom standard, you'll see the graph of the standard parabola, which is the graph of the x squared equation. And of course this is the way it's going to look on your calculator. I've got extra views here for you, but let's go back and take a look at what a does. Alright, first of all, note that the a value right now is 1. In other words, we're assuming that this means 1x squared. So let's just bump the a value up a little bit and put in a 2x square and see what happens. It would appear that the graph is a little bit more narrow than it was before. So let's try again. See if we can get a different effect with perhaps a 3x squared. And when we graph that, we see an even smaller, more narrow graph. Now this is not necessarily the effect we were looking for, but it is an interesting effect. It would appear that when the a became greater than 1, that the graph became a little bit more narrow, which is an interesting effect. Let's see if we can make it do something different. Let's go back, keep our original x squared, but get rid of the 2x squared and get rid of the 3x squared. Now since an a value greater than 1 made the graph more narrow, let's see what happens when a becomes less than 1, like perhaps a 1/2 x square. There's the original, and there we see the effect of the 1/2. If you're not sure, let's try another example. Let's make that number even smaller. Let's make it a 1/5 x square. See what happens, and as you can see, an even wider graph. So what we see happening is that an a that's less than 1, and note that we have stayed so far greater than 0, in other words we haven't played with any negative numbers, this made the graph become wider. And again, neither one of these is the effect we're necessarily looking for, so let's try some more values. Alright, we'll again keep the standard x squared, and I'm going to come up here and try a very different a value. I'm going to try a -1 x squared. Of course I could have just put in the negative sign without the 1, but regardless, when we graph it, this is the effect that we want to see, and that is that the graph gets turned upside down. We could try that with a different negative value. We could try it with a -3x squared, and you would get the same effect. It would still turn the graph upside down. So basically what's happening here is the fact that the a is less than 0, meaning negative, that is causing the graph to open down instead of up. Because remember, both times when the a was greater than 0, the graph was opening upward. So it's the negative sign that's really doing the job on the up and down. Alright? Now the next thing we need to look at on these parabolas is something called the axis of symmetry. Note that on the parabola it is a symmetric shaped graph, meaning there is a point somewhere in the middle where you could draw a vertical line and cut this graph cleanly in half. Now, a very convenient formula to have in front of us for the next example is the quadratic formula. Remember, the quadratic formula says that if this equation were set equal to 0, solutions would be x equal to the opposite of b plus n minus the square root of b squared minus 4ac all over 2a. The next thing we need to look for then is something called the axis of symmetry. The axis of symmetry is that spot where you could draw a line and cut the graph perfectly in half. The axis of symmetry occurs at x equal to the opposite of b over 2a. Notice that that is just a portion of the quadratic formula. So if we were to come up with a new example, get rid of this x squared and go with x squared plus a 4x minus 3, then looking at that graph, we notice that it's not centered right on the y-axis anymore. So it'd be nice to know, where is this middle point? Let's see if we can find it. With y equal to the x squared plus the 4x minus 3, the opposite of b over 2a would be x equal to a negative 4 over 2 times 1, which is negative 4 over 2, which is a negative 2. So apparently the axis of symmetry on this graph is at negative 2. Now we can hit the trace button and move along the graph until we are approximately in the middle of the graph, and as you can see, we're right at negative 2, sort of bouncing all around it here. So apparently the formula is right. That is the location of the axis of symmetry. So there is the formula you need to remember, and again, it's just a piece of the quadratic. Now the next thing we need to be able to do is find the vertex of the parabola. Now, the vertex, its first half, the first portion of the vertex, is the axis of symmetry. So if you find the axis of symmetry first, you've found half of the vertex. The second half of the vertex is just a matter of plugging in to the original function what you've already found for the axis of symmetry. So in other words, if we wanted the vertex for this same graph, we could say, well, the first part of it is negative 2. Plugging the negative 2 back in to the formula that was given, I get a negative 7. So the other part of the vertex is negative 7, which again the calculator can pretty much verify for us right here on our graph. And as a matter of fact, if we go to the calculate menu on the calculator and look for the minimum, because this graph is oriented upward, and follow its directions, making a guess at the left bound, coming over making a guess at the right bound, and make a guess at the actual vertex, the calculator will actually tell me that I was pretty much right on the money with my axis of symmetry guess earlier and my vertex guess. Now, next thing we need to look for is going to be an x-intercept. And a parabola can have no x-intercepts, it can have one, or it can have two. And we use, you guessed it, the quadratic formula to find that x-intercept. And while we're here, we might as well mention that the y-intercept is actually the easier intercept to find. It's actually just the c value from the original function. Alright, so with all this in front of us, what we need to do now is to find one example where we do everything that we've done here so far. So let's go ahead and look at one of those. Let's work with a y equal to 3x squared plus a 6x minus 9, and see what all questions might be asked of you and how we might answer those questions. Number 1, looking at the positive 3 up front, I know that this graph is more narrow than the regular x squared graph. Also, since the 3 is positive, I know that this graph will open upward just because that's a positive value. Alright, next question. What would the axis of symmetry be? Well, the axis of symmetry will be at x equal to the opposite of b over 2a, which is a negative 6 over 2 times 3, which is a negative 6 over 6, which is a negative 1. So x equal negative 1 is your axis of symmetry. Number 4, what's the vertex? Well, we have already got half of it. The axis of symmetry is half of the vertex, the first half. So if we take the negative 1 and plug it back in, and evaluate, we have the vertex. Okay. Next thing we might be asked for is, what is the y-intercept? And again, it is the constant that sits on the end. And of course, the y-intercept always has an x value of 0, so the y-intercept is easy to find. The last thing to do is the x-intercept, and for that we'll use the quadratic formula. In this particular case, a equals 3, b equals 6, and c equals negative 9. So x is equal to the opposite of b plus n minus square root of b squared minus 4 times a times c all over 2a. So we're going to have negative 6 plus n minus the square root of a 36 minus n minus will make plus, and 9 times 4 is 36 times another 3, 36 plus 108 all over 6, which equals negative 6 plus n minus, let's add another 36 to this, the square root of 144 over 6, which is negative 6 plus n minus 12 over 6. We'll add first, and I'll get a negative 6 plus 12, which is 6 over 6. That's a 1. Negative 6 minus 12 is a negative 18 over 6, which is a negative 3. So here we have, from the quadratic formula, our two x-intercepts. They will be a 1, 0, and a negative 3, 0. So this is basically everything that you could be asked about one of these quadratics. Now, backing up, one convenient thing about having the quadratic formula here is the discriminant. The discriminant can tell you a lot about what your graph is going to look like. All right? So let's just take a minute to go over the discriminant. The discriminant, of course, is b squared minus 4ac. And here's what we know. If it is number 1, if b squared minus 4ac is equal to a perfect square, or is simply positive. Okay, perfect square makes it easier to work by hand, but positive is good enough. This implies that the graph has 2 x-intercepts. Okay, next possibility. If the discriminant is equal to 0, that means the graph has 1 x-intercept. And number 3, if the discriminant is negative, that implies the graph has no x-intercept. So just figuring the discriminant can give you some idea of what your graph might look like.